Okay, so this is Chem 108, Chemical Principles 1 at York College. Today is March 31st, and we'll finish Chapter 5 and start Chapter 6 today. So Chapter 5, as you know, is on gases. And so we've finished all the materials, in kind of presenting all the materials and gases, but we're going to do a couple of problems before we move on. So assume CH4 gas, methane gas, behaves like an ideal gas. Find the density of CH4 gas at STP. Can you do this? I think you can do this. There's a couple of ways to do this. You can use the ideal gas law, PV equals nRT, or there's a variant of the ideal gas law that specifically addresses density and molecular weight. And let's pull that up. Right, so here's the, let's move that up, right? The formula that you might want to use. Okay, so here's the question. The question is assume CH4 behaves like an ideal gas. Find the density of CH4 at STP. So put your heads together gently and figure it out. Yeah. Value of R that has to do with liters, has to do with liter atmospheres, right? Because STP gives you pressure. You'll generally use atmospheres, 1 atmosphere. Okay, so assume that CH4 behaves like an ideal gas. Find the density of CH4 at STP. And so STP, standard temperature pressure, it's going to be 1.000, let's say 0 atm, exactly 1 atm. And the pressure and the temperature is going to be 273 Kelvin. And so go ahead. How are we going to do this? Okay, you could do it that way. PV equals nRT.
Later on it becomes D equals. Okay, if you want to use that one then.
Okay.
Use that one and it becomes D equals P.
Okay, so we got molar mass equals dRT over P. And then if we solve for D, we get D equals P.
P over RT.
Over RT.
Times M.
Times M, or molar mass, right?
So then to put it in, we get D equals 1.
Yeah, 1 atm.
Over 0.821 times 273.
821 liter atmospheres per mole Kelvin. And times 273.
And the M is 16.042.
The M is, sorry?
16.042.
16.042, and what's the unit there?
The unit,
Grams per mole. And the answer is 0.0716. And what's the unit? Grams per liter. So the ATM and the ATM cancel. The moles and the moles are going to cancel. The Kelvin and the Kelvin are going to cancel. And what you have left is grams and liters. 0.716? Okay, so it maybe depends on a little bit on 714 or 716. It maybe depends on how many significant figures you used for your molar mass. You maybe used another digit for R. So either one of those is going to be okay. Well, in this case, where's your significant figures are limited by the R that you used and the temperature that you used. We're going to take this as an exact value, right? So the exact value doesn't matter, or you can really put it in as something like this, right? Because it's not 1 with uncertainty, it's just 1. It's like there's 10 or 100 centimeters in 1 meter. That's an exact value. Yeah. Yeah.
For CH work, instead of doing that as just 16.042, you left it at 16 because you wanted hydrogen as 1 and carbon as well.
Well, you should not limit your significant figures based on your molar mass because you can get more from the table very easily. Right. So use enough significant figures in your molar, enough decimal points in your molar mass, so that's not where you kill your significant figures. Yeah. Yep.
What units it falls out?
Okay, so this is a little complicated, right? So we've got, that's a very good question, and I'm glad someone brought it up, because some magic happened here, right? To get rid of our units. We know that density should be something like grams per liter, mass over volume. So we had atmospheres, right? 1 atmosphere over 0.0821 liters atmospheres over mole Kelvin. So when you have something like this, it's kind of strange, right? Because you have something over something that's under something. So when you have a situation like this, the moles Kelvin, another way to think about is whatever's in the denominator of the denominator goes into the numerator. And so it's liters atmospheres per mole Kelvin, and so it's going to be 0.0821 liters atmospheres per mole Kelvin, right? The whole thing flipped when you put it in the basement. And then what else is in the basement here is 273 K. 273 K. And what's on top is 16.042 grams per mole. And so we're just going to keep writing it out here, 16.042 grams per mole. So the trick here is to flip the mole Kelvin up onto the top. And so when that happens, the atmosphere and the atmospheres cancel. The moles and the moles cancel. The Kelvin and the Kelvin cancel. What's left is grams over liters. So part 2 of this question says, find the molar concentration, big capital M, molar concentration of CH4 gas at STP. How can we do that? Any ideas?
Wasn't it moles per liter? You need to find the volume first.
We don't actually have to find the volume because we know this. We know the density in grams per liter. The liters doesn't change when you go from grams per liter to moles per liter. Right? So we know the density is grams per liter. And the molar concentration is moles per liter. Liters to liters doesn't change. Grams to moles, we know how to do that. How can we do that? Molar mass, right? So here you use the molar mass. So what I'm going to do is I'm going to take the density, which is 0.0716 grams per liter, and I want to get my grams to moles. So I'm going to how am I going to set this up? Is the 16.042 going to go on the top or the bottom? Bottom. Why is it going to go on the bottom? I want the grams to cancel, right? 16.042 grams per mole. The grams and the grams cancel. I have moles per liter. And oh, 0.716. Okay, there's an extra 0 here. Okay. 0.716. And so when you do this calculation, you get 0.0446. And what's the and what's the unit? Moles per liter. Or 0.0446 molar. All right, capital M. Either one of those is acceptable. Let's do another one. Balanced? Yeah. Okay. A 10.0 liter rigid vessel. Rigid means the volume doesn't change. Contains a total of 7.0 grams of N2 and 1.5 grams, no, let's call that 3.0 grams of H2. We're not using the equation yet. Okay, we're just thinking about a rigid we will use this, but but just not yet. 10.0 liter rigid vessel contains a total of 7 grams of N2 and 3.0 grams of H2. Find the total pressure in the vessel at STP. We're putting concepts together here. We're not doing a reaction yet, but we're putting a few concepts together. Sorry, did I mess that up? Okay, put your heads together and work on it. Find the pressure at standard pressure, right? At standard temperature. Right. So you know the temperature, you know the volume, you know R. You don't know N, but you can find N for each one, right? And once you find N for each one, then you have the idea that partial pressures add to give you the total pressure.
Okay, I have an idea.
Yeah. This problem here combines two concepts. One is the ideal gas law, PV equals nRT, or P equals, in this case, nRT over V. And it also integrates the fact that if you have a mixture of gases, the total pressure is the sum of the partial pressures. Right? And so you have two gases, and so you can basically you need to find the partial pressure of each. And so what I want to do is P equals nRT over V for N2 plus N of H2 RT over V. right? So P total equals partial pressure of N2 plus partial pressure of H2, right, equals N2 and partial pressure of H2. So what I need to do is find N for N2, the number of moles of N2, and the number of moles of H2, right? Because R I know, T I know, it's standard temperature, and V I know, it's a 10-liter rigid vessel. So how am I going to find the moles of N2? I'm going to use my molar mass. So the molar mass of N2 is 28.0134 grams per mole, and H2 is 0.16 grams per mole. And so when I do 7.0 grams of N2 divided by 28.0134 grams per mole, 0.25 moles of N2. And when I do 3.0 grams of H2 over 2.016 grams per mole, I get 1.5 moles of H2. So, questions so far? This question does not specify what units to report the pressure in, so you can use any variety of R as long as you report out the pressure in the right units. So I'm going to do this. I'm going to do the moles of N2, which is 0.25 times, if I want 0.0821 liter atmospheres per mole Kelvin times 273 Kelvin all over 10.0 liters. And so the liters and the liters cancel, the moles and the moles cancel, the Kelvin and the Kelvin cancel. And so atmospheres. And this equals 3.36? Or 3.36? Sorry? Okay, so no, this is just the first part. The first part, the N2. 3.36, right? That sounds about atmospheres. And this is from the N2. Right. You could have done it all at once. Right. The math says that because the R, the T, and the V are the same, this, if you distribute, you can get N of N2 plus N of H2 times RT over V. Right. You can just add these two together, the moles together, and then times RT over V. Right. That's mathematically equivalent. And that's actually quicker. Right. But conceptually speaking, because we're doing one of these, for the first time, this is 3.56? 0.56. Okay. N2 plus, yeah, that makes sense, 1.5 moles of H2 times 0.0821 liter atmospheres divided by mole Kelvin times 273 Kelvin all over 10.0 liters. Right? So liters and liters cancel, moles and moles cancel, Kelvin and Kelvin cancel, and we get atmospheres, and that's 3.36 atmospheres, and that's the pressure of H2. And when I add them together, I'm going to get 3.92 atmospheres. So P total equals 3.92 atmospheres. Yeah.
So I kept all my significant figures throughout, like everything,
Mhm.
and then I got 3.90. Is that okay? Like,
Well, actually, significant figures, so I didn't think about the significant figures. This is going to limit us to 2 significant figures, so this is really going to be 3.4. So 3.4 plus 0.56 is going to give us 3.96, right? So it's going to be 4.0. So 3.9 or 4.0 is, either one is okay. Right, depending on where you did your rounding. But correct, because when you add 2 significant figures here, you're going to end at 1 decimal place. So 4 is okay, 3.9 is okay. It depends where you did your rounding. Yep. Yeah, that's not added the molar masses, no, because you have different amounts of each one, right? So if you add the molar mass, you have, you're saying that both nitrogen and hydrogen have the molar mass of like 30, right, which isn't true. Right? The nitrogen and the hydrogen have to be considered independently of one another. So you could have added the moles once you did this. You could have plugged straight in here 1.75. Yeah, yeah. What did you get?
I got
0.390. That sounds like you have a power of 10 somewhere missing. So we can look at it at some point. Yeah. Yeah, we can look at that sort of during the break. Okay, so let's leave this here. Let's call this, okay, so that's good. So let's leave, where should we leave this? We should leave this leave all that information up there, or at least leave that information up there. And let's do the next part of the problem. And this is where it gets actually even more fun. If the reaction goes to completion, find the limiting reactant. Find the pressure of NH3. Find the mass of NH3. Okay, so if the reaction goes to completion, right? So find the limiting reactant. Find the pressure of NH3, partial of pressure NH3 when the reaction when the limiting reactant is all used up, and find the mass of NH3 when the limiting reactant is all used up. So you finished the last exam and forgot all about limiting reactants, right? Yeah. So what do we have to do? We have to ask ourselves if, remember, you just calculated this, right? You start with 0.25 moles of N2 and 1.5 moles of H2, right? So once you know the moles, to find the limiting reactant, it's no different from any other reaction. So what we want to do is say, let's say all the N2 is used up, how much product do you get? Let's say all the H2 is used up, how much product do you get? And so we're going to say, if all the N2 is used up, we're going to have 0.25 moles of N2. What am I going to do now? coefficients. 1 mole of N2 produces 2 moles of NH3. 1 mole of N2 produces 2 moles of NH3. And so that's going to give me 0.50 moles of NH3. Could be produced if all the N2 is used up. And then I'm going to say if all the H2 is used up, I'm going to get, so I start with 1.5 mole of H2. And what goes here? Yeah. 3H2, 2 moles of NH3. So 2 moles of NH3, 3 moles of H2. And so that's going to get me 1.0 mole of NH3. So which one is the limiting reactant? N2. So N2 is the limiting reactant because less product can be made. So we found the limiting reactant. Can we find the partial pressure of NH3? Well, we've got to make the assumption that the temperature doesn't change. We know that the volume doesn't change. So, and we know how many moles of NH3 there are. Can we find the pressure? Yeah. So then we're going to take this and use it in P equals nRT over V. And we're going to say 0.50 moles times 0.0821 R times we ran out of space, nRT over V equals 0.50 times 0.0821 times 273, right? All over 10. And that's 1 point what? 1.12 something. Actually, it's just going to be 1.1 because we have two significant figures here. So 1.1 ATM. So that gives us the partial pressure of NH3. And let's find the mass of NH3. Can we do that? How do we do that? Well, we know the moles still. So the molar mass of NH3 is 14 point something plus 14.007 plus 3 times 1.0079, is that right? Yeah. 0.0079. 17.0. 0.14? That doesn't seem right.
Because H could also be 1.008.
1.008.
Could also be 14.
Okay, 1.00794. Okay. So we're going to say it's 17.0 because that's enough significant figures because we're limited here, right? Nope, we're limited here, two significant figures. So it's going to be 0.50 moles of NH3 times 17.0 grams of NH3 per mole of NH3. Right, we just need to use enough significant figures here so we don't limit our answer. And so that's going to give us 8.5 grams of NH3. And so we found the mass of the NH3. We're not going to do this calculation right now, but I want you to try this at home. Find the total pressure in the vessel after the reaction. No, we found the pressure of the NH3, but there's something else that's left. What's left? The H2 is left over. The N2 is the limiting reactant, so the N2 is all gone. But there's some H2 left. How many moles of H2 are left? And based on the moles of H2 that are left after the reaction, what's the partial pressure of the H2 that's left after the reaction? Right, you take that and you add it to this, and you get the total pressure after the reaction. So try that at home, or try that during the break, which we're going to take right now. Okay, so instead of having you do it at home, I wrote out the answer here. So the moles, this is the aim. This is where we're getting. Right, the total pressure after the reaction equals the pressure of the product, partial pressure of the product, which is the NH3, which we solved for, plus the partial pressure of the excess, which is the H2. And so the partial pressure of the product we got, right, that's the 1.1 atm. So what we need to do is find the partial pressure of the excess. How do we find the partial pressure of the excess? Well, we use PV equals nRT on the moles of excess. How do we get moles of excess? We get it like this. Right, the moles of H2 that you start with, 1.5 moles. Right, that was from before. That was from here. Right, minus the H2 used up. How do we know how much H2 was used up? Well, we start from the limiting reactant, 0.25 moles N2, and we use the coefficients. 1 N2 requires 3 H2, and that gives us 0.75 moles of H2 used up. Right, so you started with 1.5 moles of H2. Once all the limiting reactant was used up, you also used up 0.75 moles of the H2. And what's left is the difference. 1.5 minus 0.75 equals 0.75. That's how much H2 is left. Once you know how much H2 is left in moles, you plug that in using the formula that we've done a whole bunch of times to get the ATM. Right, that's just like above. Get the pressure. That's the partial pressure of the H2. So what's the total pressure left? It's the pressure of the excess, that's what's left, plus the pressure of the product. So it's 1.7, that's the excess, 1.1, that's the product. Add them together, you get 2.8. Okay, so after spring break, we'll do a few more review problems now here and there in gases, just to keep you kind of on the ball. And because gases also integrate with the next topic, which is chapter 6, or the next chapter, which is chapter 6, which is called Thermochemistry. Thermochemistry, as you might sort of surmise from the name, has to do with kind of heat and energy, and how heat and energy relate to chemistry. And so let's think about energy a little bit. Right? Energy is, we kind of have common definitions of energy, right? You know, didn't have enough coffee, so I'm low on energy, or you know, I didn't sleep enough, so I'm low on energy. I ate too much sugar, so you have a lot of energy. But energy, chemically speaking, or scientifically speaking, is the capacity to do work. And work of course, also has a common definition. I have a lot of work to do. There's chemistry, Alex is too much work, that kind of thing. Work, scientifically speaking, also has its own definition, right? And that's basically moving something. One way to look at it is moving something against a force, right? So energy is a capacity to do work. What are some types of energy that you know? Heat? It's, sorry? Mechanical energy. So that's the energy of kind of moving things, moving parts, yeah. Sorry? Kinetic energy. So that's the energy of motion. We talked about kinetic energy as it relates to gases. Potential energy is energy as it relates to the position of an object or how much energy is stored in an object. Chemical energy. So chemical energy is, we usually think about that as chemical potential energy. That's how much energy is stored in chemical bonds, for example. And so things like gasoline and heating oil and TNT, right? that have the ability to release a lot of energy when they're, for example, burned or blown up. They have a lot of chemical energy in them. So here are some others. Radiant energy, also known as solar energy, right? It comes from the sun, primarily from the sun, and is the Earth's main energy source. Almost all the energy that we get comes from the sun, right? That's the initial source. Thermal energy, the energy, this is essentially where heat comes from. It is the energy associated with the random motions of atoms and molecules. Chemical energy, the energy stored within the bonds of chemical substances. Nuclear energy, energy that's stored within the collections of neutrons and protons in the atom, in the nucleus of the atom. Nuclear energy is something that we revisit in Chem 2, if you take Chem 2. Potential energy, energy available by the virtue of an object's position, right? So if I have an eraser, I lift it up high, now I've raised it against gravity, right? Gravity is trying to pull it down. It has some potential energy. If I were to attach a string to it and pull it over a pulley, when I dropped it, it would be able to pull up an object, right? And so that's the capacity to do work. These may not be all the sources of types of energy that exist, right? But these are just some examples. Or there may be kind of subclasses of these, right? So we talk about like things like geothermal energy, energy from water, right? Hydropower kind of energy. All sorts of different types of energy. The capacity to do work. Okay, so I haven't put up slides in a while, so I'm going to put up slides for the last chapter plus chapter 5 plus this chapter. And so we're going to focus, the point of that is you don't have to write all this down because the slides are coming up, are going to be on Blackboard. So we're going to focus in on energy and chemical reactions in this chapter. Right? You have all sorts of different energy, but we're going to look at, basically, we're going to live in this area mostly, right? Thermal energy and chemical energy. Right? Heat is not exactly energy, right? But heat is the transfer of energy, the transfer of thermal energy between two bodies that are at different temperatures. Remember when we were talking about kinetic molecular theory, and I asked you about, I forget what the gases were, like hydrogen and carbon dioxide, both at, 300 Kelvin. I said, which one has molecules with the greater kinetic energy? And some of you said carbon dioxide, and some of you said hydrogen. And I said they're the same, right? Because they're at the same temperature. So the point there was the molecules have the same energy if they're at the same temperature, and you can kind of extract from that if they're at different temperatures, the molecules would have different energies. So basically, if you put two objects in contact that are at different temperatures, sooner or later what's going to happen? The one that's hotter is going to lose energy to the one that's colder. The one that's colder is going to gain energy from the one that's hotter until they both reach the same temperature.
Would molar mass have an impact on what goes faster? Would TA have like a
On speed, it does, yes. Molar mass, at the same temperature, the higher the molar mass, the slower the molecule. But bigger molecules intrinsically have more energy, right? It's mv squared over 2. So it's mass and velocity, and they cancel each other out, so that the only thing that affects it is the temperature. Temperature is a measure of the thermal energy. Right? The higher the temperature, the more energy the molecules have. But they're not exactly the same thing. Right? We talked about this when we were talking about intensive and extensive properties. Do you recall this? Right, so what are intensive properties and what are extensive properties?
intensive is like color, right? And so if it's not as
Like a weight.
Right, so intensive depends or doesn't depend on the amount of substance, right? Intensive does not depend on the amount of substance, right? So something like density doesn't depend on, or malleability, right? They don't depend on the amount of substance. Something like mass or volume does depend on the amount of substance. Those are extensive. So we talked about energy versus temperature. Right? One of them is extensive and one of them is intensive. Or heat and temperature. So let's look at it this way. Which one is temperature extensive or intensive? Does it depend on the amount of stuff or not? No, it doesn't. Right? If I set a piece of paper on fire, it's going to be, I don't know, let's say 1,000 Kelvin or 800 Kelvin. If I set the room on fire, it might also be the same temperature, 800 Kelvin. Which one has more energy? You set the room on fire, right? Because there's more, basically, molecules. Right? Each molecule has the same energy, but there's way more molecules, so you get way more heat, way more energy. The heat or the energy depends on mass. The temperature does not. Right? If I set a small fire or a big fire, the temperature could be the same. But if I set a small fire, the amount of energy is a lot less than if I set a big, enormous fire. So thermochemistry is what we're going to look at. It's a study of heat change in chemical reactions. And when we think about thermochemistry, we have to be very careful about what we're talking about, what we're considering, because it's about heat being exchanged from one place to another place. So we have to be very specific about what the place is or what the item is that we're considering. And so the thermochemists talk about a system, right? The system is the specific part of the universe that you're studying. And if you're studying a glass of water, the system is the water, right, or the glass of water. The surroundings basically, oh, nope, we didn't get to surroundings yet. There are a few types of systems. You have an open system. So what you have here is like a bottle of water that's open, no cap. So what can exchange? Matter can exchange, right? So water vapor can go out. Right? If you heat up the water, what's going to happen? Water vapor is going to go up and out of the bottle. And because it's just like a thin piece of plastic or glass or something, heat can go in and out. So you're able to exchange both matter and energy, mass and energy. If I put a stopper in it, right, and seal it real tight, it's still this kind of cheap plastic where heat can go in and out, or glass where heat can go in and out. But now, as long as the seal is tight and it doesn't blow up, right, nothing can get out. And so energy and heat can go in and out, but matter cannot. So that's what's called a closed system, where only energy is able to get in and out. And the next kind of system we have is this. And this is kind of what we would think about as an insulated vessel, something like a thermos bottle, where, at least in theory, right, your thermos bottle is supposed to keep your drink hot. Right? So energy is not supposed to be able to get in and out, nor is matter supposed to be able to get in and out. And that's called an isolated system. So neither matter nor energy is able to get in and out of an isolated system. So there's a lab that you do, I don't think you've done it yet in 109, where you use a styrofoam cup. Right? The styrofoam cup is supposed to approximate, at least on the time scale that you're working, an isolated system. Right? So it's supposed to keep all the energy inside the cup. Of course, we know the styrofoam cup isn't perfect. After a few hours, it'll cool down. But you're working just on a couple of seconds to a couple of minutes, right? So on that scale, very little energy is able to get in and out. Nothing, yeah. So the system is the specific part of the universe that's of interest in whatever experiment you're doing and whatever problem you're doing. The rest of the universe is called the surroundings. And in principle, the surroundings is basically what's close by. Or in practice, the surroundings is what's close by. But in principle, it's really the rest of the universe. So we have some terms to kind of define. Exothermic process is any process that gives off heat. In other words, it transfers thermal energy from the system to the surroundings. And so here we have hydrogen gas combining with oxygen gas to give you water. This is actually a very important process that may become quite a bit more important in the future. Right? So has anyone heard of the Hindenburg? And this was this German blimp, I don't know, probably close to 100 years ago now. It was filled with hydrogen gas. And we just learned that the density of gases depends on its molecular weight, right? So hydrogen gas has a very low molecular weight, so its density is going to be quite low. Right? If the density is quite low, that means it's going to float on air, right? Because oxygen and nitrogen makes up most of your air. So these days we use helium in blimps, right? Helium also has a low molecular weight, but back in the day they used hydrogen, right? And hydrogen has an even lower molecular weight and therefore a lower density than hydrogen, than helium. So, but the problem is hydrogen explodes. And so there was this terrible explosion, the blimp blew up, lots of people died, and then they started using helium. When it blew up, what happened? It released a lot of energy, right? And stuff caught on fire, and lots of bad things happened. What scientists are trying to do today, and some of you may know, actually, Dr. Small, the lady who substituted for me once, one of the things she works on in her research is controlling this process, right? So if you can control this process so you don't get an explosion, but you get the controlled release of energy, you can do things like make a battery, produce energy for electricity or for your car. And why is that good? That's good because besides energy, the only product is water. Right? These days, if we want to get energy, most of the time, what do? We burn gasoline, we burn oil, we burn all sorts of stuff that releases carbon dioxide and other greenhouse gases, other pollutants. But if you could have a process where your only product was water, pure water, that would be wonderful, right? Because the water is not polluting. And actually, there's lots of places where you need water. So being able to control this in a cost-effective manner, control this kind of reaction in a cost-effective manner is a very active area of research. A less kind of impressive release of energy is something like this, right? When you condense anything from gas to a liquid, or you freeze it from liquid to solid, you release energy. Endothermic process. Endothermic process is the opposite of exothermic. So any process in which heat has to be supplied to the system from the surroundings. And so the opposite process, right, liquid to gas, when you boil something, you want to boil water, you want to make soup, what do? You have to turn on the heat. You have to put in an external source of energy. Different examples. Mercury oxide, tons of exothermic and endothermic processes. If we think about it another way, an exothermic process, once it's done, the environment is going to be hotter. Right? An endothermic process, once you're done, the environment is going to be colder. Okay, so here's what we call energy, some energy diagrams. And this kind of diagram, this is kind of the beginning of diagrams that you'll see if you go on and take Chem 2, if you go on and take organic, or maybe some physics, physical chemistry. Here you have energy on the vertical axis. You have low energy on the bottom and high energy on the top. And so if you recall from the slide before, right, no. Right, HGO is an endothermic process. The breakdown of HGO to Hg and O2 is endothermic. Nope, sorry, wrong. We're looking at this one. H2O plus O2 gives you H2O is an exothermic process. That means it gives off energy. Sorry about that. We got H2O, H2 plus O2 plus H2O. Right? So if it's giving off energy, what does that mean? That means the system, which is the hydrogen and oxygen, when it becomes water, is losing energy. Right? The system is losing energy because the energy is going from the system into the surroundings. Right? So the hydrogen and oxygen atoms are the system, and energy or heat is going into the surroundings. So if it's going into the surroundings, it's being lost from the system, and so the system is going from a higher energy to a lower energy. The mercury and oxygen is the opposite, right? So as mercury oxide gets broken down, it's an endothermic process. What does that mean? That means energy must be taken from the environment, that is from the surroundings, and it must go into the system. So if it's going from the surroundings into the system's energy is getting more energy. So it's going from a lower energy state to a higher energy state. Yeah.
At any point, would they become equal?
What do you mean by that? That's a yeah.
The heat within and the surroundings, do they become equal?
if you have an open system or a closed system where you're able to exchange heat, and you leave stuff alone, right? You don't like add a source of heat or add a source of cooling like a refrigerator or something, then eventually everything will equilibrate, yes. But in this case, what you're doing probably is like putting it on a burner or something, right? So you're adding some more heat. That's why it's going up. Right. And then eventually once, well, yeah. Oops, wrong computer. Okay, so we talked about thermochemistry. Thermodynamics is a scientific study of the interconversion of heat and other kinds of energy. We're going to look at this a little bit here. And then in Chem 2, those of you who go on to take Chem 2, there's going to be a whole chapter on thermodynamics. In order to understand thermodynamics, we need to think about what's called a state function. And a state function, as the name kind of implies, refers to something that where you're looking at particular states of a system. What does that mean? Let's say you're climbing a mountain, right? There might be two interesting states, right? The first state might be you at the bottom of the mountain, and the second interesting state might be you at the top of the mountain. If you're talking about a chemical reaction, the two interesting states might be the reactants and the products, right? So if you're thinking about the hydrogen plus the nitrogen gives you ammonia, one state might be hydrogen and nitrogen, the second state might be the ammonia. And so state functions are properties that are determined by the state of the system, regardless of how that state was achieved or how that condition was achieved. So some state functions are things like energy. So these two hikers started, there's two of them up here, right? They both have the same initial state, and they both have the same final state. Their potential energy, in other words, how much energy if they kind of like jump off the mountain and they hit the ground down here, is just defined by how high they are. In other words, if I wasn't mountain climbing, if I raised the eraser, and it doesn't depend on what path they took. So I took the eraser and I raised it like this, and I took the eraser and I raised it like this to the same height. Once I get here, it has the same amount of potential energy. That's a state function. So the blue person and the red person, once they've reached the last state, they have the same amount of potential energy. Right? They both what's not a state function? What's not a state function is the linear distance, right? The distance that they had to walk, the number of steps they had to take. Right? The red one took a much longer path than the blue one. So the potential energy of hiker 1 and hiker 2 is the same, even though they took different paths. That's an example of a state function. Mathematically speaking, we can describe that like this. Right? Delta E, this little triangle is the Greek letter delta, capital delta. And that stands for the change. Right? So the change in energy from here to here is a state function. And it can be described as the energy at the final state minus the energy at the initial state. Right? State functions are defined by their states, right? By where they are. So it doesn't matter whether it's red or whether it's blue. The change in energy just depends on the two states. And so here are some other state functions. Pressure, right? Volume, temperature. So if I start with a little, an uninflated balloon, and then I blow it up to this big, the volume is the same would be the same as if I started with the uninflated balloon, blew it up real big, and then let some of the air out. Right? That's kind of obvious. Same with pressure. Right? If I add pressure, then or add it slowly or add it quickly, the pressure is the pressure once I get to the final state, temperature, and so on. And so all of those we can look at like this, right? Because they're state functions, we can think about their change defined by the final versus the initial. Delta P, delta V, delta T. There will be a couple of others, some of which, maybe one or two of which we'll learn about in this chapter, and some more of which you will learn about if you go on and take Chem 2. Questions so far? Okay, so what we're doing so far is just largely defining terms, introducing concepts. Pretty soon we're going to start applying them in kind of more real ways to chemistry, to matter, and to reactions. But questions so far? Okay. So the first law of thermodynamics, this in some sense reflects the first principle of atomic theory. Right? The first principle of atomic theory says that matter, atoms, cannot be created or destroyed. First law of thermodynamics says energy cannot be created or destroyed. Right? It can be converted from one form to another, but you can't make energy, you can't get rid of energy. Mathematically speaking, this is one way to define the first law of thermodynamics. If E represents energy, right, and we've just thought about delta E in the last slide, the delta E of the system plus the delta E of the surroundings for anything that happens must equal 0. Right? Another way of stating the first law of thermodynamics is the total energy in the universe never changes. Right? It doesn't go up, it doesn't go down. Right? It's not created, it's not destroyed. The only thing that happens is its form changes. Right? When the Hindenburg blew up, what happened? The chemical potential energy, or the chemical energy in the H2 bonds, got converted into things like heat and light, different kinds of energy. So what does this mean? That means whatever your system is, if the energy of the system goes up, the energy of the surroundings must go down by an equal amount. If the energy of the system goes down, the energy of the surroundings must go up by an equal amount. If you're boiling water, right, if you have like a gas stove, right, you turn it on, you get a little flame, the energy in the fuel gets converted to heat, which heats up the water. Right? Energy is changed from one form to another, but cannot be created or destroyed. So if that's true, then mathematically speaking, this is also true. The change in energy of a system equals negative change of the energy in surroundings. Right? You just, mathematically speaking, you can do the subtraction, or you can think about it. Right? If one goes up, the other one must go down. And so this is what we're talking about, right? So this is C3H8, right? C3H8. Anybody know what that is? That's propane gas. And so propane gas is the gas that you use in a gas barbecue grill, for example, usually. And so if you burn it, you release heat, right? And that heat can then go to like cook your food or whatever. The chemical energy lost by combustion, right? Here's the system, right? The system is the chemicals. And exothermic reactions release energy to the surroundings, right? And if they release energy to the surroundings, the energy of the system goes from high to low. But what about the surroundings? The surroundings is like your hamburger. It gains energy, right? It goes from low to high. So this is one concept that students sometimes have trouble with, right? Exothermic reactions lose energy, right? And so students very reasonably kind of might think, okay, if something loses energy, it should get cooler. But when you burn something, it gets hotter. And that's because you're not separating, because when you're burning something, it's hard to separate often the system from the surroundings. The system is the stuff you're burning. That actually is losing energy. What's getting hotter? What's getting hotter is the surroundings. Your grill's getting hotter, the air's getting hotter, your hamburgers are getting hotter.
So would the gas in your barbecue be getting, the temperature would increasing or no?
See, in that case, it's not actually, the energy that's being lost is the energy that's stored in the chemical bonds, right? So that's chemical energy. So would it be getting colder? Right, that's why where it kind of gets hard to say. It's not really getting colder because the energy there is potential energy, right? So it's stored energy that's getting released, right? So what's happening is these molecules in their bonds have a lot of energy. These molecules in their bonds don't have a lot of energy. And the difference, when you get from here to here, gets manifested, gets expressed as heat and light. Another way to look at the first law of thermodynamics is as follows. And so we're looking at delta E, right? Delta E is of the system minus delta E of the surroundings. Now we're looking at a system. Right? The delta E of the system, the change in energy of a system, equals Q plus W. What is Q plus W? What's Q and W? E is a change in internal energy. Right? Q is the heat exchange between the system and the surroundings. And W is the work done on or by a system. So, it's an easy formula to memorize. Delta equals Q plus W. But what does it actually mean in terms of English? Right? So if something happens where the energy of a system changes, right? For example, you burn stuff. And two things can happen, right? One thing that can happen is that Q can happen, right? Heat can go from the system into the surroundings. But the other thing, remember, what is energy? Energy is a capacity to do work. So if instead of heating, in some sense, when you grill your barbecue, you grill your hamburgers, you're doing a little bit of work, but not that much. But if you really want to do work, you can do something like, instead of putting your fuel in your barbecue grill, put your fuel, different kind of fuel, of course, into your car. Right? And you put your fuel into your car, it also burns. And what happens when the fuel in your car burns? Well, inside your car is something that looks very roughly like this. Right? One of these piston-like things that that we thought about when we were doing gas laws. So you may get some increase in pressure, but really what you do is you get an increase in volume. Right? And what does the increase in volume do? The increase in volume, well, this thing is attached to something that then eventually turns some gears that moves your wheels. Right? So as you burn stuff, right, your volume in your piston increases. Right? And then that is work being done. Right? So either the heat change, the energy change goes to heat, or it goes to work, or some combination thereof. right? And in the engine of your car, it actually does both, right? You turn on your car, you drive for a while, the engine gets hot, but it's also doing useful work. And there's many different types of work, but the most common type of work, or the simplest type of work to think about, is what we call P delta V work, right? And so there's a constant pressure on the piston in your car, and you push against that pressure, what's going to happen? The volume's going to increase. So work equals what we call negative P delta V. We'll think about the negative sign probably on Thursday. Positive and negative signs mean very specific things when we're thinking about thermodynamics or thermochemistry. So work is P delta V, negative P delta V, when a gas expands pushing against some pressure. And so here's the sign convention. I guess we'll think about it now. So if there's, let's do the work later. Let's think first about the heat, right? If you have an endothermic process, that is, let's say you have a pot of water and you turn on the stove and the water starts to get hot. The water is your system. And so the water is absorbing heat from the surroundings, right? The surroundings in this case is mostly the stove, right? So the water is getting hot. It's an endothermic process, and the sign is positive, right? So that means heat, Q, would be positive for an endothermic process. If you have an exothermic process, that is, the heat's going from the system into the environment, into the surroundings, the heat is, Q, would get a negative sign. And so when you have something like the combustion of hydrogen to give you water, right, the fuel cell reaction or the Hindenburg reaction, and the hydrogen oxygen is your system, the sign on Q, the sign on your heat, when the oxygen or when the hydrogen burns would be negative, right? So whenever heat or whenever energy is going into the system, the sign is positive. Whenever energy is going out of the system, the sign is negative. And so if you understand that, when you think about the work, it might be a little easier. If the system is doing work, right? If you are doing work, what's happening to your energy? You're losing energy, right? Energy is going from you into whatever you're doing, right? If you're lifting weights, if you're doing your chemistry homework, your energy is going out of you into what you're doing. So if work is done by the system, the sign is negative because the energy is going out. Just like if you burn something, energy is going out. The sign is negative. And so the opposite is also true. If work is being done on the system, then energy is going into the system, and the sign is positive. Okay, so here's this is where we'll stop. On Thursday, we'll actually think about specific examples of heat and work.